Good morning, everyone. Welcome to our first lecture on spectroscopy. This word may look big and difficult, but it is actually simple. Spectroscopy is just the study of how light interacts with matter. Light is all around us: the sunlight, the colors of a rainbow, the brightness of a bulb. Matter is also all around us: the air we breathe, the chair we sit on, the water we drink. When light meets matter, something happens. The light may be absorbed, it may be reflected, it may scatter, or sometimes it may even be given back as a glow. By studying these effects, scientists can understand what the matter is, what it looks like inside, and how much of it is there. So, spectroscopy is like a special language that molecules use to talk to us. And today, we will learn how to understand that language. Spectroscopy may look like a big scientific word, but its meaning is quite simple. The word comes from two Greek words: spectrum, which means image or appearance, and scopein, which means to look at or to observe. So, the original meaning of spectroscopy was looking at spectra or observing images. Today, it refers to the study of how radiation interacts with matter. Now, what do these terms mean? Radiation is not just the visible light we see with our eyes. It includes many forms of electromagnetic energy, such as ultraviolet light, infrared radiation, microwaves, radio waves, and even high-energy X-rays. Matter is everything around us, and it exists in different forms: solids, like metals, crystals, or even a piece of wood. In solids, atoms and molecules are tightly packed. Liquids, like water, oil, or alcohol, where particles move more freely than in solids. Gases, like oxygen, carbon dioxide, or the air we breathe, where molecules are far apart and move very quickly. All these types of matter can interact with radiation, but the interaction may look different depending on the state of matter. When radiation of a certain energy falls on matter, the matter responds. By observing this response, scientists can learn about its structure, composition, and properties. Three important things can happen when light or radiation meets matter. Absorption: the matter takes in the energy. Molecules move to a higher energy level, almost like climbing to the next step on a ladder. Emission: molecules cannot remain excited forever. When they fall back to a lower level, they release the extra energy, often as light. This is why stars shine and why neon lights glow. Scattering: instead of being absorbed, the light may simply bounce off or change direction after hitting matter. The blue color of the sky is a result of scattering. These three processes, absorption, emission, and scattering, form the foundation of spectroscopy. By carefully measuring them, scientists can identify unknown materials, understand the structure of molecules, study chemical reactions, and even analyze the composition of distant stars and galaxies. In short, spectroscopy is a powerful tool that allows us to see the unseen by studying how different forms of matter interact with radiation. To make this clearer, think of two simple tools. A magnifying glass helps us see tiny details of an object that are invisible to the naked eye. In the same way, spectroscopy magnifies the hidden details of matter: its atoms, molecules, and structures, details that cannot be seen directly. A stethoscope allows a doctor to hear what is happening inside the body, like the heartbeat or the flow of air in the lungs. Similarly, spectroscopy acts as a listening device for matter. It listens to how matter absorbs, emits, or scatters radiation, giving scientists clues about what is happening inside at the molecular level. So, spectroscopy works both like a magnifying glass to reveal the unseen and like a stethoscope to listen to the hidden signals, making it one of the most powerful tools in science. To understand spectroscopy, we first need to understand light. Light is part of the electromagnetic spectrum, which you can imagine as a very long line or ruler. At one end are waves with low energy, and at the other end are waves with very high energy. Here are the main types of radiation along this spectrum. Radio waves, very long, low-energy waves used in radios, TVs, and mobile phones. Microwaves, shorter waves used in ovens to heat food and in satellite communication. Infrared, IR, felt as heat, like warmth from the sun or a fire, also used in remotes and thermal cameras. Visible light, the rainbow colors our eyes can see, from red to violet. Ultraviolet, UV, invisible but causes tanning and sunburn. Also used for sterilization. X-rays, high-energy waves that pass through soft tissue but not bones, used in hospitals. Gamma rays, the strongest, produced in nuclear reactions, used in cancer treatment but dangerous in high amounts. So, the electromagnetic spectrum covers everything from the gentle radio waves to the powerful gamma rays. Spectroscopy studies how matter reacts when these different types of radiation interact with it. In chemistry, we do not use all parts of the electromagnetic spectrum. Instead, we focus on only certain regions because each region gives us different kinds of information about matter. Ultraviolet, UV, and visible light. These regions are used to study electronic transitions in molecules. When molecules absorb UV or visible light, their electrons move to higher energy levels. This tells us about the electronic structure and is very useful in UV-V is spectroscopy. Infrared IR radiation. This region is used to study bond vibrations. Different chemical bonds like O-H, C equals O, and N-H vibrate at specific infrared frequencies. By analyzing IR spectra, we can identify functional groups in a molecule. Microwaves and radio waves. These lower energy radiations are used in nuclear magnetic resonance spectroscopy. They interact with the nuclei of atoms, such as hydrogen or carbon, allowing us to learn about the arrangement of atoms in molecules. X-rays. These very high-energy waves are used in X-ray crystallography, which gives us the exact 3D arrangement of atoms in a crystal. This is how scientists determine detailed structures of complex molecules like proteins and DNA. So, in chemistry, different parts of the spectrum act like different tools, each designed to reveal a specific type of information about atoms and molecules. When light meets matter, three main things can happen. Absorption. The molecule takes in the energy of the light and moves to a higher energy level. Example: imagine climbing up a staircase. You need energy to move up each step. Similarly, a molecule absorbs light energy to jump to a higher level. Emission. The molecule cannot stay at the higher level forever. It eventually comes back down to a lower level and releases the extra energy as light. Example: just like walking back down the staircase, the molecule releases energy on its way down. This released energy often appears as visible light. Scattering. Sometimes the light does not get absorbed at all. Instead, it changes direction after striking the molecule. Example: imagine throwing a ball at the staircase wall. Instead of being absorbed, it bounces off in another direction. That is how light scatters. These three processes, absorption, emission, and scattering, form the foundation of spectroscopy. Imagine a staircase with steps going upward. An arrow going up the stairs represents absorption. The molecule absorbs light energy and climbs to a higher energy level. An arrow going down the stairs represents emission. The molecule releases energy as it comes back down. An arrow that bounces off the side of the staircase represents scattering. The light does not enter but changes direction. So, the staircase helps us visualize energy levels. Up equals gain energy, absorption. Down equals release energy, emission. Bounce equals change direction, scattering. Now, let us look at the first type of spectroscopy, UV visible spectroscopy. It uses ultraviolet light and visible light. Molecules that have conjugated double bonds absorb strongly in this region. Example: carrots look orange because of a molecule called beta-carotene. This molecule absorbs blue light. Since blue is absorbed, the carrot looks orange to our eyes. Applications: used to study colored compounds, dyes, and pigments. Important in food science, textile dyes, and drug research. So UV-V is spectroscopy is like asking molecules, what colors do you absorb? By knowing that, we can understand their structure. The second type is infrared IR spectroscopy. This uses infrared light to study vibrations of chemical bonds. Every functional group vibrates at its own unique frequency. That is why IR spectra are like fingerprints of molecules. Examples: alcohols show a broad peak for OH. Ketones and aldehydes show a sharp peak for C equals O, around 1,700 centimeters to the minus first power. Applications: IR spectroscopy is used to identify functional groups in organic molecules. It helps confirm if we really have the molecule we think we have after synthesis. So, IR is like a musical instrument. Every bond is like a string that vibrates at its own pitch, and IR tells us which strings are vibrating. Now, let us move to one of the most powerful tools, NMR spectroscopy. NMR uses radio waves and a strong magnetic field. Certain atoms, like hydrogen and carbon, respond to this by giving signals that depend on their chemical environment. Example: in ethanol, NMR shows three signals: one for the CH3 group, one for the CH2 group, and one for the OH group. This means NMR doesn't just tell us what atoms are there, it tells us how they are connected to each other. Applications: NMR is used to study small organic molecules, but also huge biological molecules like proteins and DNA. In organic chemistry, NMR is the main tool for finding out the structure of new compounds. Another important method is mass spectrometry. Mass spectrometry measures the molecular weight of a compound. It also breaks molecules into fragments, and these fragments give us clues about the structure. Example: aspirin has a molecular ion peak at 180. It also shows fragments that confirm the presence of ester and carboxylic acid groups. Applications: MS is used to confirm molecular weight. It is useful in drug development, forensic analysis, and environmental testing. So, mass spectrometry is like a puzzle. The machine breaks the molecule into pieces, and by studying the pieces, we can reconstruct the original molecule. The final major method is X-ray crystallography. This uses X-rays to study the exact 3D arrangement of atoms in a crystal. When X-rays hit a crystal, they form a pattern. From this pattern, scientists can calculate the positions of every atom. Example: the most famous discovery, the double helix structure of DNA, was found using X-ray crystallography. Applications: used to study proteins, enzymes, DNA, and inorganic crystals. Essential for modern drug design and biochemistry. X-ray crystallography is like a 3D camera. It takes a snapshot of molecules at the atomic level. Each spectroscopic method gives us a different piece of the puzzle. UV-VIS tells us about conjugated systems and electronic transitions. IR tells us about functional groups like OH, C equals O, NH. NMR tells us how atoms are connected inside the molecule. MS tells us the molecular weight and fragments. X-ray crystallography tells us the exact 3D structure. If you combine them all, you get the full story of the molecule. It's like solving a mystery with different clues. Why is spectroscopy so important? Because it is used everywhere in science and daily life. Structure elucidation. When scientists make new compounds, Spectroscopy is the main tool to confirm what they made. Real world applications, pharmaceuticals, confirm drug structures before they are used. Forensics identify unknown powders, poisons, or drugs at crime scenes. Environmental chemistry detect pollutants like heavy metals in water. Biochemistry study proteins, enzymes, and DNA. Everyday life MRI scans in hospitals, sunscreens that block UV, testing food for safety. Without spectroscopy, modern science and medicine would be blind. Spectroscopy is especially important in organic chemistry because it allows us to study molecules in great detail without destroying them. It helps us in three major ways: identifying unknown compounds. Every molecule has its own unique spectrum, like a fingerprint. By examining the spectrum, we can find out exactly what a substance is. Confirming structures. When chemists synthesize a new molecule, they need to make sure it really has the structure they intended. Spectroscopy acts as a proof checker, confirming whether the bonds and functional groups are in the right places. Quantitative analysis. Spectroscopy not only tells us what is there, but also how much is present. This is extremely important for checking purity, measuring concentrations, and ensuring that medicines or chemicals meet safety standards. In short, spectroscopy acts like a detective, identifying compounds, a quality checker, verifying structures, and a measuring tool, quantifying amounts, all at the same time. With this, we conclude today's session. Thank you for listening, and I hope you now see how spectroscopy helps us see the unseen in chemistry.